Then I select variable. In this case, my photo is my variable. I give a start value. Let's give a start value of a femtoampere and an end value of a nanoampere. Once we have done that, you guys just need to click on this OK and then click on this green button and it should simulate your circuit. So I'm going to leave this as it is in case people need to add something, and then I'll come over and have a look to each one of you. Guys, we have half an hour to finish and we will finish in half an hour or else I'll kick you all out. Launch ADEL. That's the first one. That's it. Okay. Then click on variables, copy from cell view. Okay. You have got photo, give it a value, 1 pico. There. Now first you need to say what you, something has happened wrong. So we have got a voltage and a mu. So you have written 3.3 volt, right? It is automatic. If you don't write anything, it automatically gives the units. Okay, if you write V, it thinks V is a variable. That's 1 mu. Where else I have got? 3 micro. And after every change, we go and save it. Okay. Now let me delete these. Now what is the value of this photocurrent? We need to give some parametric sweep, right? This is the one which we are going to sweep. And now we do copy from cell view. Okay. Now you are plotting this, that we don't. Let's give it a value of 1 pico. And now you say outputs to be plotted. Select on the design. I select that value as my output. And then you say what kind of simulation I want. I want a DC simulation. I want to change a design variable. I want to change photo. Don't worry, I'm doing too quickly, but in all of these it's kinda intuitive. And I say you sweep from 1 femto to 1 nano. And then you simulate. Ooh, something is not right. What have we done wrong here? You don't need to draw this big wire. You could have just called it VDD-I. VDD is also a global signal. Okay, let me see what have gone wrong here. Did I swip the current source to be in this size? That does not make sense. Sense. Sorry? This point, just above the current source. What error have you done? Why is my voltage going up? Okay. Let's have a look. Let's have a look. So what I'm expecting to see is a logarithmic response between input and output. So let me see which direction is. Okay, my diode current is in the opposite direction. See, one of the things that you have to see, you cannot get more voltage than the power supply which you are providing. So if things are going up, that's not expected, right? So I'm getting a logarithmic response. So till here it's dark. Here you can see the scale is log and it's going down. Actually, a better way would be, got it? Goody? Got it? Okay. The only thing which you have not done is you haven't told where to see the output. I want to see the output at this point. Okay. That's it. Let's simulate, and if you have done everything correct, hopefully we will get a result. We're not getting a result. What have we done? M2 is referencing to an undefined. Ooh. What? This should not cause a problem. M2, M0, M1, M0. So which is M3? M2, M1, M0. Everything is problematic. Bravo, what have we done? Ah, okay. When we designed it for the first time, which is yours? Which one? Did you type UMC 118? Oh boy. Why do you have a different installation here? Yeah, that's all right. Why does this computer has a different? No, there is UMC 180 nanometer. That is all right. So that I can see it more clearly. The circuit is correct. It's not a circuit problem. This is basically saying it cannot see the libraries, and it cannot see the libraries because I can't see the libraries. For some reason the setup does not have the libraries. I can manually add it a library. But that's not how it should be done. Okay, I will add manual library for the time being, okay? UMC 18 nanometer is there. It's in home. So I'm manually asking it go and read there. Oh boy, somebody has played nasty things with this. So no, it's not your fault, it's the machine. I'll fix it. I will fix it. I think it should be this one. Let's see if that does the job. Problem is here. There are different people who have come on different days. Where is the error? That is the error message. Oh, crap me. Every time you make a change, you need to save it. When you started Cadence, who started Cadence? Somebody else did it? You sourced the technology file, right? Because right in the beginning it does not see the variable path. What are libraries? MM180. Ouch, sorry. Let's see if that does the job, or else I will have to ask you guys to come back after lunch. Okay, I've done something. One error. Okay. Oh, this is just the resistor. Okay, no. Okay, I don't want the resistor. I want the transistor MM180 diode, and then we need that's low voltage, that is, yes, Reg 180, low voltage. Okay, which is the main process file here. Zero threshold voltage, resistors 33. Low voltage. Core. No, that's core RF. V2. Okay, I need to open it and check it myself. One of them should have the transistor definitions. Typical. Okay, let's see if that does the trick. Yes, that does the trick. So I manually set it so that to get your output. The library files are missing. Okay? Yeah. So I'm getting an output. See? Cadence is always fixable, it just takes time. What happened, guys? What's going on? Ooh. Ooh. That doesn't look like a block pixel. What has happened here? Can you show me the schematic? Photo going down. May I have a quick look? Okay, first thing first, your diode is very big. So let's make it slightly smaller diode, okay? That should maybe do the trick. No, it does not do the trick. So what have we done wrong? Oh, you gave all of these. I generally don't this it. I just leave it on its own to run. One pico to a micro. Let it do an automatic sweep. Still, that looks okay. Still does not look terribly good. An atto to a micro. So this looks fine. This does not look fine to me. It should not go till 3.3 volt. Oops, that explains. You guys have used a 1.8 volt transistor, right? And we are simulating this circuit with what power supply? The transistor is burning. So we had to select the 3.3 volt transistor. This transistor is not characterized to work at 1.8 volts. After that it just goes whoopsie. So if it was real circuit, you would have seen bzzz. So change these two to 3.3 volt transistor as well. Okay? Right, what happened? You should not have to do that ever again. That's one-off thing. Quite frankly speaking, right in the beginning it should be set by itself. But if it is not set, yes, just increase the range a little bit. Okay? That doesn't look like. You have 11 millivolt output. See? That does not look right, does it? So no, the other way around. This is NMOS. So invert the diode, reduce the size of the diode. Diode is too big. Okay? So make it 3 micron. Make it 3 micron. But then flip the diode. Okay? Okay, dokie. So you guys have got your output. You have your output. You have your output. You don't have your output. I'm hungry now. What happened? So, what do you want to do? You need to see what do we want to plot? We want to see this value as an output. Okay? And then we want to say what kind of simulation we want. We want a DC simulation. We want to start at say 1 femto or even 1 pico, and we want to go till 1 micro. Let's go till micro. Yes, that looks like a logarithmically. So I'm feeding a photocurrent which is this value, and I'm getting a straight line, which means what's the response here? If the x-axis is logarithmic, y-axis is 1 pixel. Certainly it's a pixel, but it's a large pixel, right? You have got a lot of empty gaps here.
Yes.
So other than connected everything, let's do a DRC check. Can this be manufactured? So go to Asura and do run DRC. Just click OK. Everything should be set. If it's not set, we will know anyway. Yeah. And now you want to view the results of the run? Go. So there are already 3 errors which it is saying. Your minimum metal 1 area has to be this much. Minimum diffusion to contacts. You only have 3 errors. That's impressive. But now we need to go and fix these errors, right? This is basically saying you have poly 1 somewhere extending. So zoom it here. So you see there is a small gap here. That is saying it cannot make that gap. So we connect it this way and the error gap will go. You have just drawn it here. So these small gaps is smaller than the minimum size transistors which it can make. Guys who do regular chip design, the PhD students here, he has only got 3 DRC error. For the first layout, impressive. But he has only got 3 errors. Is it? Is it? That's cheating. I thought he is very good layout. There's only 3 errors. When I did my first chip submission, the chip was error free. It went to fabrication, came back. So they do their own checks. The foundries does its own check before sending. They send a 93-page error report. And the message was something like this: it's Friday, please fix it by Monday morning. You only received 4 comments, right? I received a 93-page one. So what are the comments? Metal density error? And the logo is not acceptable. So we, yeah, okay, that's fine. Okay, so it's CDAC is doing it. So CDAC manages Europractice, is it? So you don't submit directly to Europractice, you submit to CDAC. Okay. As this is SCL. Okay, I would like to know what the result is, because I haven't seen a chip coming back from SCL. I've done PhD Viva wherein people have sent their chips.
It's taking 6 to 9 months.
It never comes back. So once it comes back, I would like to know, because it's not a bad process. The process is good. Good. What happened? That's not right output for 2 reasons. Look at the voltage which you have got. What's the voltage? Don't forget it. What's the number? 20 volt. I'm giving 3.3 volt in my chip. I cannot get 20 volt. Agreed? So let's see what have we done wrong here. Can I? So it's already saying some warning messages to you. 9 warning messages. Never leave warning messages by themselves. See daisy. So this should have been ground exclamation mark. So if you make it exclamation mark, it connects it to the global ground. Otherwise it thinks it's a new signal of its own. Okay, and this will also be VDD exclamation mark. Okay, if you do that, call me. Okay, we have got a result. Well, this was the question which I am going to ask you guys in a minute, and then we will see whether it's a right or not result. Where do you want to plot? So you want to see some output. Okay, so let's select this line on my output. This should be ground exclamation mark, or else you are having warning messages. Okay, so make it ground, press Q, select escape, press escape. Now press Q. So what I will do is I will delete all of these and do it again. Much better than trying to figure out. And these two are not connected. Okay? So you only have 9. So these lines, all of them should have a name. Similarly, ground exclamation, and this should be VDD exclamation mark. Okay? Once you have done that, then run. Okay. Here is a question to all of you guys. So if you have done it properly, what you would have got is on your x-axis result, photocurrent, which should be in 10 to the power minus 12, 12 to the power minus 9, 8, 7, so on and so forth. And that's in a decade scale, right? It's 10 times. On your x-axis, you have a linear scale. Okay, you have got 2.7, 1.8, so on and so forth voltage. So what's the relationship between x and y? What kind of relationship I expect to see? My x is logarithmic, y is linear, and my response is kind of straight line. So what will be the response function? If it was a straight line, both x and y were linear, my function would have been y is equal to mx plus c. Straightforward. But now my x is logarithmic, so what will be my function? Exponential. Why don't you fit those, see, and see what will be the line of exponential? Why should it be exponential? So my slope is negative. M is negative, right? It's not a positive going slope, it's a negative going slope. But it's not be exponential. It will still be y is equal to mx plus c. Just in place of x, we have log of x. Okay. So now here's a task for those who have already got. Ignore the leakage current line. Just look at the line in between. Okay. Look at your output line, and if I have to model it as y is equal to m log x plus c, what is the value of m and c from your waveform? How will you go about finding it? Okay. Right. Should I have a look at your layout? Okay. Yeah. I love fixing DRC errors. Okay. So first is the DRC error, then will be the LVS error, which will come later. I think there is a short somewhere. This cannot be true. So first this VDD and this should be connected, right? If you look into your schematic, where is your schematic? This poly and this is connected, isn't it? Okay, let me see what I can do here. See, you have got these pins. They are saying what is VDD, what is row select, out, and so on and so forth. Let me just have a look here. So according to you, this metal is just connected to this metal, is it? Was it the error? This gap. Well, most probably not. Okay. So why don't we move it? Then you have to move everything, right? Let's see what other error we have. It will take a minute. Small chips take quickly, but when you have two errors, minimum poly on field is into diffuse. Where is it? Where is it? Sorry?
The body connection is missing.
That's fine. I don't think it's body connection which is problematic for him. There is something else which he has done here. So one is this metal one area that I know that's my fault. So this is just saying it's a metal one which is flying out for no reason. Okay. So what we could do is we could draw a metal one. That will fix it. Ideally, this is just saying this metal one is not connected to anything, kinda. What's the next error? See the error? No, you see this is coming till here. This cannot, so it's trying to make a small gap. It does not know what it is, right? It says this small gap I cannot make. So if I were you, I will just take poly and just damn fill this gap. Or make this slightly bigger. Will that do the job? Gravity, hate gravity. So this is basically telling me I can only move it in 0.1 decimal places. That should go, right? And then the error is, yeah, I think I'm done. Let's go and make it. How much money do you have to make this chip? Yeah, tell me how much it will cost me if I try to make an array of these pixels. If I was in industry, it would cost me, oh, there's still a damn error. Okay, I can fix that. You know what, when we moved it that side, this thing whole moved this side. Okay. So what I can do is stretch. Stretch. I'm saying stretch, don't move. Undo. F. You know what? The next easy thing is to move this damn transistor a little bit. Let's see if that fixes the errors. At least this says that this circuit can be made. It doesn't say whether this circuit is correct or not. Yes! We have no DRC errors. But it does not say whether this is the same circuit as our simulation. For that we have to do layout versus schematic. Okay. At least you have got DRC free circuit. I think we can let him go home, right? Not the best circuit, but the foundry will not reject it. I know there is no ground contact, but once the whole chip is made, there will be a ground contact somewhere anyway. So in Pixel Mini, often we don't give ground contacts. It just takes area. Okay, has anyone got a number? What's your number? 1.8 plus M is minus. Okay, that's C. What is the unit of C? Can't be volt. Ah, sorry, C is volt. And M would be? I'll be back to you in a second. What happened? Have you got your result or not yet? Oh, you did get your results, right? Okay, all those who have got a logarithmic response can leave now. It's already 1 o'clock, so it's lunch hour for you guys, and we'll meet after 2:30 to do sensor characteristics lesson. It's a trick question. Again, what's the x-axis? So what's the unit of log? Precisely. So essentially, you cannot have a plot which is log of I, because I has got a unit. So you're essentially doing plot of log I divided by 1 ampere. You're normalizing it. Volt per decade, you can say. So in 1 decade, how much it changes. So that will be the unit. Okay? Well done. What about you guys? Goody, goody, goody. Got it. Right, go and have lunch. What about those two there? Got it? Go and have lunch and then. We have to make them close enough, but you saw when you make them too close, it's giving warning that it cannot make. It was giving those errors, right? Yes. So you have to make them close enough that we don't get those errors, but as close as possible. Okay? And then not only you need to think it this way. Right now you have placed one transistor up there, one transistor. Should I place all the 3 transistors in one line? Should I place them in the corner? There are many ways of placing the transistor and the diode, right? I mean, think of it this way. The other thing which you are thinking is, so let's save it, okay? Let's create a new cell. Where's the library? Which transistor is yours? Kiran?
Kiran.
File, new, cell view. And I want to create a array 2. Let me just call it array 2 for the time being, okay?
Okay.
Now, when I create an array, what was it called? The first one, Kiran layout?
Layout, yes.
And now what I will be doing is I will be creating some, let's just do it 5 by 5. Now what you need to think about is not just my pixel. So I need to think about what my neighboring pixel will be. So if I place it here, I need to give some gap for the neighboring pixel to move that side.
Yes.
So can I place the two transistors of this and the two transistors of this in one row? Will that be better? So it becomes a multi-dimensional optimization problem. So you need to think. Earlier you were just thinking for one pixel.
Yes, yes.
Now I have these three of this, these three of this. Can I place both of them on one side so that they take less space, and this side there's nothing there?
Yes, yes.
Should I place them in corner, side? Should I place them in L-shaped corner? Or many times what we do is we first put the transistors and then say, okay, this is the smallest area in which we can put the transistor. My diode has to be, my pixel has to be 5. Whatever is left, I fill it with diode. It doesn't matter it's 2 micron or 3 micron or 2.75 micron. Okay? To the neighboring pixel. So we don't connect. So what we do is now we can do edit in place. So now if I'm going to just edit this one here, and you wanted the VDD to be connected, right?
Yes.
VDD is in which metal? Metal 1.
Metal.
So let's just take metal 1, a path, and connect it till this point. So I edited one pixel, and automatically all of the pixels got edited. Now metal 1 gets connected.
Connected. So this is, that's it.
Well, there is more to it. A, first minimization. B is always big gap between pixels. So other than that, it is it. Well, we haven't checked whether this is the layout or not. It's not. There is an error. I have already seen the error. But other than that, this is it. That's the array part. Rest all you design scanners separately, and then you come and see chips like these. Come here. So what we will do, so most chips have got a pad ring. You see this ring here? So this is called a pad ring. At the end of this, we have got these contact points. So we go and solder to these points, because the chip transistors are very small. We need to take them out as a big contact to connect to the rest of the world. So your array will go here. We'll connect the array to the pad ring, and out goes. That's.
Where is the diode?
So this is not a diode circuit.
Okay.
Your diode is how big? 3 micron.
3 micron.
This area will be a few, well, that's 2000 micron, that's 2 milli. You will not see the diode in that. Right? So if you have got 1000 by 1000, you won't see inside one anymore. You have to zoom in quite frequently. Okay? Right, guys, if you really want lunch, you have to go, or else you will stay here hungry, and this will be a fast